Explanations on how and why things work are aimed to assure that they work as intended. This assurance is a large part of certification for automated systems that are safety critical. In aerospace, regulations prescribe that such systems come with evidence that they do what they are supposed to and don't do things that might be dangerous. A key concept is the traceability of requirements. Tracing the links up and down the hierarchy of requirements gives us an explanation for every bit of code. But what about artificial intelligence? Is it possible to trace the internal structure of the AI code to requirements? If not, does that mean you can't predict what it will do in a given circumstance? AI is a marketing term covering a bunch of technologies. These systems use supervised machine learning. Here, computer programs called neural networks recognize images from the cameras installed on aircraft. For example, one component of Daedalean's visual traffic detection is a neural network that decides if an image contains an aircraft or not. We trained it by giving it millions of images labeled by humans. This is called a training dataset. The job of the neural network was to extract statistical patterns. If you ever calculated the linear regression in high school, you did the same, but you only used two parameters, say alpha and beta. You chose the best values for the parameters by looking at the differences between predicted and measured values. Neural networks do the same, but use millions of parameters instead of two. If you pick the optimal values for alpha and beta, now you can predict a weight from a height for somebody not from the training dataset. But there may be nobody in the new test dataset with this weight, or there may be multiple samples with different weights for the same height. So for the unseen data, we expect a non-zero error. Same thing here. The neural network says yes or no for aircraft presented on this image. It will give the same answer again if given the same image again. But this answer can be wrong. We expect a non-zero error, but what is important is how this error is distributed. If the dataset we used was a good sample of the unseen population, we expect it to be distributed as we saw when we tuned the alpha and beta parameters. But if the sample we trained our model on was wildly unrepresentative of what it will meet in the real world, all bets are off. So how often the algorithm will be wrong in a real flight depends on the right training dataset. Remember that we are talking about a machine-learned component of an application of standard architecture. This implies two sets of requirements. First, all the standard requirements for hardware and software remain unchanged. We should prove they work as intended, meet existing standards, and are safe. But this says nothing about how correct is the answer of the neural network. So we need a separate set of requirements assuring the output of the system. The critical point here is that how well it fits reality is a matter of statistics. This is the nature of the problem, not the nature of the solution. Even if our training dataset was accurate, there may simply not be enough information in small images to make the call. There are approximately 1 followed by 2,466 zeros possible images in our input space. Between any image that we would clearly label yes and one we would clearly label no, there are insanely many images that differ only by 1 bit in 1 pixel, which are on a decision boundary. The system requirements will have to be statistical. Machine learning is currently the only feasible way of solving problems with this kind of unavoidable uncertainty. We must establish statistical bounds on how predictable the system works based on an accurate statistical description of the inputs. This will be one of the pillars of certifying machine-learned systems. In traditional software, if we find a combination of inputs for which the system did not meet the requirements, we can find a bug, fix it, and prove the correctness of a program for certification purposes. With a neural network, if we find an example of a wrong output, we can run through the network and reconstruct precisely why it happened, which neurons or which pixels influenced the model to set some parameters wrong. But this is exactly how the training algorithm works when it turns the knobs for tuning parameters. We already possess the maximum traceability of the outcome to the individual parameters. Okay, what if we found a specific case in our test dataset where we got an error? Should we add it back to the training dataset? Would this work like bug fixing in a classical software program? No. This will break the independence of our datasets, adding bias towards this margin case. Any attempt to create more rule-based, more explainable versions of machine learning will cost us the capability of dealing with input uncertainty. The systems will work worse, and we can't prove they are fit for purpose and safe. Let's remember the requirements for a system as a whole, to be designed to perform its intended functions under any foreseeable operating condition. How can we cope with one component of a system having limited accuracy? By designing the system properly. One of the images most probably will be recognized wrongly, but the system doesn't rely on any single image. It analyzes many shots per second and has a new opportunity to detect a hazard with every frame. As a result, the overall performance is better than that of a human pilot. But how can we be sure that the performance we measured on a dataset will be held under all foreseeable operating conditions in the operational domain? This crucially depends on how you selected the dataset. Was it sampled from the same distribution you will find during operation? Any statement on the performance of the machine-learned component is meaningless without specifying the performance on what dataset and how this dataset was drawn from reality. Now, a machine learning aerospace engineer, additionally to the standard certification requirements, will have to explain why the dataset is representative and sufficiently large. This is not new to safety-critical engineering. Impact resistance testing to parts of aircraft has statistical nature. We just need to accept that from now on, this applies to software too. And then we can certify neural networks-based applications on more reliable grounds than explainability.